Hello everyone, let's get started. It's 6 p.m. at PST. So what was the topic for tonight? Let's see. Oh, logical multiplication. Okay, is there any question on this part or anything else from you guys? Yes, no, maybe. How is the project going on? Is good? Okay, why don't we do one quick poll about the project status? Maybe let's wait for a couple of more minutes for other people to join. There are 16 tonight. And yeah, that's maybe some more people will join in a few minutes. So one thing possibly you need to understand is a register. Like we talked about this on this multiplication logical circuit, we talked a lot about the registers, but we haven't really studied about the register, what is that component and what behavior. We'll be studying that in details in 147, how it is constructed and different types of it and how the things works inside it. But at least let me give you some quick overview of the register component, what they are, and whatever you need to understand the multiplication and the division module with that. So that's okay. With that, let me first quickly also check our discussion section if there is any question there. Seems like no. Okay, so let me share my whiteboard with you guys. Okay. All right, so register is a storage component. Like you heard of this memory and already worked with some register file that you know of. And of course, you are using those assembly instruction, add, subtract, multiply, etc., which are a register bound operation. You are storing things in the register, which are 32-bit, etc. So you are somewhat little bit know about the register, what the register is. But for you, the register is more like an hardware component that you can manipulate the value with the software commands, like all these R type instruction or I type instruction, stuff like that. In hardware world, when we call a component register, it means actually more than that. It is just not some component, some part of the register file that you are manipulating using the assembly program, but it is a component widely used inside the microprocessor uh, implementation. When we build up a microprocessor inside, like even without this register file, the other components will have these sequential elements of register. In fact, we can think in a very crude sense, the memory device that you use in your day-to-day system, like this onboard memory card, the chip goes inside that, you can view that as well uh, as a bunch of registers inside it. So in a sense, register is described as a hardware component which can store information in it. And what is the term it store information with? They are all in terms of bit. So there are so we have this small 1-bit component, like let's say if I can draw with just a square, and this component can have these things, like it is a it is a sequential element, means in a very crude sense its operation depends on a clock signal. Clock signal is drawn like this to indicate it's a clock signal, but nonetheless this is a clock signal, and we all know what is a clock signal is. We have studied that in very beginning of the semester. So this guy's operation really depends on the clock signals, and then it has just a one bit, let's say call it a D for data, and it has a control signal, let's say called L. So D is data 1 bit, and L is the control signal called load. So if L equals 1, then the output bit, let's name it Q. Q is D. Else Q is previous value of Q. So in a sense, if there is no load, okay, if there is no load, not a load equal to 1, it preserves the whatever being stored inside this component. And this can store either 1 or it can store 0 inside it, 1 bit. And this guy is called 1-bit register. This is I won't say it is the smallest component or lowermost component, but it is somewhat very low level component. In 147, we'll actually open up this 1-bit register and we'll see what inside it and how it is implemented and so on and so forth. But for our purpose of understanding, this is sufficient. There is a component, very low level, called 1-bit register. It's a hardware component, which has very, in general, it has a data, incoming data. So this is input. It's a control signal called load. It has output Q, and its operation is depending on the clock signal. Means, like, what does it mean? What this clock comes in this whole functional definition there? It's basically if L equal to 1 and let's say clock equals 1. So if clock equals 0, even if the L is 1, nothing would be loaded into that component. So far so good. Any question from any of you? Okay.
Oh, Professor, just clarifying, Q over here represents what's stored in the box, right?
Yes, exactly. Okay, now given that very basic component, now we can actually make like multi-bit register. Like we can just have that register just think if this register, okay, let's talk about 4-bit. So you are arranging this lowest component in a series, and you are declaring that this is your LSB side bit. So each of them is 1 bit. This is your LSB side bit, and the other part is MSB side. Just you are declaring that, okay, this is this one. I will say this represent this register stores my most significant bit, and this register stores my least significant bit. And each of them then has these terminals called called D. Let's just point them out. That has D. So each of them has D. Each of them has load, and each of them has Q. So D, output Q, output Q. Yeah, we have, I'm not showing the clock signal here because just assume there is a clock signal, but important is this load signal. And we have load signal over here. We have load signal over here. We have load signal over here. And now, imagine, so this is your register, let's say 3, register bit 2, register bit 1, and register bit 0. And they are storing, let's say, 1, 1, 0, 0. So essentially, these 4 together, assuming this is MSB and this is LSB, this is representing a value of 12, right? Decimal value of 12. Now, imagine there is this external line, let's say some line, input line is coming up from some other component in the computer. And they are setting this incoming data is 0, 1, 1, 0. And there is one control signal, some component is controlling all the load together. Load signal. So now at this point, if I have issued a load equal 1, then what will happen? It will basically go and load this new value into the register. So your value now represented here is nothing but a 6 in decimal. And then you just turn this guy to 0. So now even if some external component changes these, let's say this bit to 1, which then together it represents a value of 14, your internal storage will still be 6 because your load is 0. So you can really control what values to be loaded in parallel in this configuration. Right? So far, any question?
It appears not.
Yeah, seems like. Okay, so far so good. Now together, you just imagine together this whole thing, if we just call it a register, right? Together it's a 4-bit register. Let me send it back. So together this is a 4-bit register. And this guy has what? This guy essentially has a queue of 4-bit output. So you can imagine this is all out going up, going out of this component. It is incoming data, which is 4-bit, and 1 bit of load signal. And of course, there is a clock. So I didn't mention showing the picture, but this is your 4-bit register. As a schematic symbolic diagram, you can just place it. But internally, it has 4 individual 1-bit register bit, and they are controlled by this load signal together. So that, and it can do insert it can store the data in parallel. So this is like parallel in or parallel data loading. Okay, parallel data loading. Okay. Now, next part would be what about the shifting? How we can actually shift the bits inside this register things. Let's take another example of bits. Okay, so this is like, let's put together simple 4 bits. We have 4 bit of registers, 1 bit each, and we have like we have this D, Q, L, D, Q, L, D, Q, L, D, Q, L. Let's say this is my register 3, this is register 2, this is register 1, and this is register 0, 1 bit each. And now imagine it has one external data, 1 bit. Okay. Load is common. They're controlling these guys. And now the trick here, just see by the configuration, this output is connected to this input. Okay. And let's say internally it started with a value all zeros. When we start up the circuit, it has internal value of 0. So it represents a decimal value of 0. Now you place a 1 here, 1 at the data, and this is load, and you place load equals 1. Now what happens in each clock cycle, what will happen that these data will be written over here, this data will be written over here, this data will be written over here, and this data will be written over here. Okay, so let's place that 1 here. And now in the next clock cycle, so 1 clock cycle gone, the next one at this point, what will happen, this one will come over here. Okay, let's do it another way. Okay, this 0 will conceptually go out. This 0 will come over here. This 0 will come over here. This 0 will come over here. And this one will enter, stored into there, conceptually. Now, next clock cycle, we are keeping the load as 1. Next clock cycle, at this point, this guy will just go out. This one will go over here. This one will go over here. This one will go over here. This one will store into that one. So you see, as if we are actually shifting the value through towards from the MSB to LSB, which means that we are shifting right, doing a right shift operation in this with just by connecting Q to next stage D, Q to next stage D, right? So this is a left shift register. So if you just put together, this is a 4-bit left shift.
Wait, Professor, do you mean right shift?
Oh, sorry. Thank you very much, Rahul. This is right shift. Right shift. And similarly, we can actually make a left 4-bit left shift. How we can make it? There, our configuration would be something like this. This queue will be connected here. This queue will be connected here. Just the opposite connection. This queue will be.
Professor?
Yes.
Just confirming this I mean this type of right or left shift register will take if it's in if there are 4 registers, it'll take 4 clock cycles to load a complete value into it.
Exactly. Yes.
Okay.
So, okay.
So is it more, I mean, on the manufacturing side, is it more convenient to just have, I mean, on the front of the is it more convenient to have a shift register that will take n number of clock cycles to load completely, or is it more convenient to have uh, like add in the extra wiring and create the extra circuitry to create the register which has a shift capability and can be loaded in one clock cycle?
Yeah, that's a very good question. It really depends on at which part you are actually applying that register. Okay. So
Okay.
some of them can start with like some initial value all zero, and it really needs 1-bit shift at a time for separate purpose. Some of them will be reviewing on 147, but that's a good question. Okay.
Or rather, to be more, since you say it depends on where you use it, in the multiplication circuit, we use left and right shift registers.
Exactly. Exactly.
So in that circuit, is it? I mean,
So
is it worth?
usually I know where you are going. So usually what happens, we can actually combine this functionality with parallel load functionality together. We'll see it in 147 how we can do it. So in that way, we can really build by combining parallel load and shift registers. We can really have a component ultimately which has like a, let's say, 4-bit parallel load and parallel out. We can have something like, we call it a scan in, the single data, this shift scenario, we call it a scan in that case. And then it will be inside, these things will be stored in sequence like that. You imagine like per clock it will shift one bit to another, and in that case it has also something called scan out. So scan in, b, scan out, and we have possibly 2 bits of mode selection. Okay,
So
so
one for loading data, one for scanning.
exactly. So mode 0, maybe this is like hold the data, whatever you are storing, store it. Then maybe mode 1 is parallel load. You load it, parallel load it actually from the D. And then we have mode 2 is shift right. Okay, so you are inserting the bits from the most significant bit side and just repeal carrying it through, just propagating it through all the bits in the register, 1 bit per clock, bit by bit. And the other way would be right.
Shift left.
Yeah, shift right. So in that case, this guy will be propagated from this side on LSB to
Okay.
LSB side. So this is a little bit complicated construction, and we'll learn it in 147 how we can construct that. Now, depending on your application, what you are trying to do, what you are trying to construct in the hardware, you just pick up your convenient component there. Either all parallel load is sufficient for some scenario.
Is it sufficient
Just
for the ALU, at least the multiplication logic,
Mhm.
or does it increase the time too much?
Multiplication logic, if you look at that sequential multiplier, actually you need kind of part parallel load, because you need to load the multiplicands in parallel, multiplier in parallel, like parallel load, and
Yeah,
then you need to shift it. So basically you kind of need combined register
I
thing.
see.
Mhm. Yeah, right.
All
So
right, that makes sense.
these are all about the register that you need to know, that there are registers which can together can do parallel load, can do shift right, shift left, and internally it somewhat looks like this. Now, how this is done in detail, we'll be studying in 147 class. Any other question? Okay. So now, okay, now since I think all of you are here in this session, let me just do a quick polling on your project status. So this is multiple choice, and this is, you can take it anonymously. Okay, so you don't need to reveal who you are there in that poll. Just I'm interested in data as a whole class. Where are you? So there are components. Okay, let me launch the poll and explain, and then you can vote. Okay, so so you see there are like multiple option, and you can choose between where you are. Right? Probably you haven't started. Just click one. Probably you have completed the normal ALU, logical addition, subtraction. So click three on of them, and so on and so forth. So choose multiply. You can choose multiply and can poll it anonymously. So please do it in a minute. We'll see where, as a class, where are we? There are 18 of 20, maybe three more, two more, 19 of 20, one more. Okay, so we are done. Now let me share the result and to you and see. Okay, 45%, almost half haven't started that. Guys, you have a day, I think it is coming up exactly 1 day, 1 week, 2 days, like 9 days you have in your hand, and you can go into pretty sneaky, challenging debugging scenario in that completion of the project. So make sure you start right now after this class to do it. Like this may not be a easy breezy for you guys. ALU completion, like 40%, normal ALU, that's good. That means you are familiar with the setup and everything. 45%, wow, how come like 40% completed normal ALU and 45% completed logical addition? So maybe some people actually will do the normal ALU later. Maybe that's what my guess would be. Logical subtraction 35%, logical multiplication 15%, 3 of out of 20. No one has touched logical division. Okay, that's okay. So it is probably after the next class you'll be more clear on the logical division and how can you do that. And completed report writing, maybe I would have added one more, like started report writing. But anyway, I hope like some of you have in parallel also doing the report writing. That's also will take some time. Given that we have 1 week, 2 days left, please make sure to put more steam onto this project work. All right. Any question on the project side or on the theoretical side?
By go ahead.
Yes.
Could you just go over the two's complement procedure?
Two's complement for the multiplication.
Yeah.
Okay, we can go about that one. Let me just hold on. Where is it? Two's complement, bit replicator, two's complement is negative. Oh, okay. So there are some tricky things. Okay, let me explain. Share. So let's do one by one. The first thing is to create a two's complement, which is, I'm assuming this is like a 32-bit two's complement procedure. So I'll just taking a screenshot and upload. Okay. Right. Okay, so this is the first one to do it. This is a 32-bit two's complement. This is really your 32-bit two's complement. And this is somewhat easy to implement. It takes this one argument in it, A0, number which needs to be the two's complemented. And then return would be on the V0. So use your add logical and not to compute. So you need to invert the A0 with a not, I think not in the MIPS. Just try see what is that. So you need to do use that instruction to invert the bit pattern. And then for this addition, call your add logical from here. So don't use a add function there or add I function in any case there. Okay, so use the add logical. And since it is a procedure, all the storing, restoring, including that, it probably approximate 20 line of code. You can do it in less number of line or more number of line, doesn't matter. This is kind of a ballpark, how many line of code you need to write. Like so far, so good. Troy?
Yes.
Okay, now the next one is two's complement if negative. So this guy uses your the procedure you just created here. So let me just screenshot, save to. Okay, so this is the next one. So in this procedure, you are basically going to call this procedure internally. You're going to call this procedure internally. But before that, it's a two's complement if negative, right? So how do you test if it is a negative number or not? Since we are actually following two's complement format, means you need to test your MSB. You need to really test your MSB of your number. So let's say this is your register, has 32 bits in it. Just test this guy. So you can extract the bit and then you have, remember you have a macro to extract the init bit. So extract the 31st bit from there, extract, and then test if it is 1 or 0. So if it is 1, then if this guy is 1, then call this, then do the compliments. So this is also good. Okay. Next would be this thing. This is little bit involved. It is a 64-bit 2's complement. So you need it for your multiplication because multiplication result is 64-bit, and you need to complement that. And complemented 2's complement of 64-bit is not combination of 2's complement of 32-bit. It's more than that. So let me explain it. The third one then is this. Just where is that? Okay, that's the next one. Okay, this is the next one, 2's complement. Now let's take a 4-bit, 8-bit example. Like let's say there are 2 4-bit values. Okay, maybe it is 0, 0, 1, 1, 1, 0, 0. And you need to make a 8-bit 2's complement. But what you have is a procedure for, so you have procedure for a 4-bit 2's complement. So exactly what it is needed to be done here is this, right? You invert the bit pattern for 2's complement on 4-bit. You invert the bit pattern and add 1 on top of that, right? So this is 1 plus 1, 0, 1 plus 1, 0, 1 plus 1, 0. This is 1, 0, 0. And just for the fun, let's calculate the 2's complement for 4-bit for this pattern. So you invert it and do a plus 1. Now if you think, okay, now this is together, it is my 8-bit 2's complement, it's fine. Maybe for this case, it's fine. Let's see. 0, 0, 1, 1, 1, 0, 0, 0. So you need to really make inversion plus 1, which is, I think this is same, 1, 1, 0, 0, 1, 0, 0, 0, 0. This is fine as the same thing. Let me think another. Okay. Okay, let's say we have 4 bits like this. Okay. 0, 0, 1, 1, 1, 1, sorry, 0, 0, 0, 0. Okay. So its 2's complement is going to be like you need to invert this bit 1, 1, 0, 0, 1, 1, 1, 1 plus 1. Now you need to addition this thing 1 plus 1, 0, carry over 1, carry over 1, carry over 1. Now this would be your 2's complement for 8-bit, but if you, just for the fun, if you do it individually, That means just calculate 2's complement for here, and 2's complement for here. Hey, this is not, this is also the same. Oh, no. This is, no, this is same. This is also same. And what would be another example? Let's see. You are carrying 0 plus 1. That's interesting. Why don't we do this thing? Let's take 5-minute break. Let me think an example where it breaks. Okay. Then, like, individual 2's complement won't give us same as whole 2's complement. Okay. Let me think. And let's take 5-minute break.
Professor,
Yes.
could you open a breakout room?
What's that?
Could you open a breakout room?
Beka what?
Could you open a breakout room? I wanted to ask you something, or rather inform you of something.
Okay. Okay. Sure. Yeah. All right. Let me see how we can do that. Rahul. Okay. Add a room. Okay, assign. To one. Okay. Okay, what I'm doing, I'm opening up rooms for all of you, and I've created one for Rahul. Wants to ask me something. I'll just join that room, okay? But we are having an official 5-minute break now. Okay, let's get back to our discussion. Now I know there is one example of that scenario. Okay, so see this one. So let's take this bit pattern. 1101 and 1000. So its 2's complement would be 00100111 plus 1, which will be 00010100. This is like if you do the complement 8 bit together. Now, if you think you are doing it individually, then each of them would become like 0010 plus 1, 0111 plus 1. Now see that this computation is not same as this computation because of this extra plus 1. So that means if you are bound to do a 4-bit computation at a time, but you still want to do a 2's complement of this bit of the whole 8-bit, what you need to do, you need to take, instead of addition plus blindly, whatever carry out is coming out of this point, you need to add it here. And that's how you can make sure that your complement computation is correct. So that's what we are trying to do in the 64-bit 2's complement, where we invert both A0 and A1. Both are 32-bit, and since it is a 32-bit processor, we cannot use any function beyond 32-bit capability, right? So it is the same scenario as this guy. We cannot, let's say cannot operate beyond 4-bit, but we still want to compute 2's complement of 8-bit. It's the same scenario. So what we'll do, we will invert both, then use add logical to add 1 to the A0 and intercept the carry out from that addition and add that carry out from the previous step to A1. To do that, you must also upgrade your add logical procedure to return the final carry out bit in the V1 register. So V0, it's the summation, and let's upgrade the add logical to return the final carry out from the addition operation on the V1 register so that you can capture it during this step and send it to this addition. Does that make sense, Troy?
Yeah, that makes sense. But I have one more question.
Yeah.
For the 32-bit 2's complement, do we store and restore the A0 and A1 after we change it?
Yeah, it's a procedure, right? So if you are changing in any sense, then you need to do store and restore.
Okay. Thank you, Professor.
No problem, Troy. Brian, you are going to ask something?
Yeah, I was curious about the late policy for if we turn in this project a day late or anything like that.
Was that all? What?
If we turn in the project late, what happens?
There is no let turn it
Okay.
in.
All right.
All right. Okay, now what? 6:55. Let's have a pop quiz. Let me set this up. Set this up for you. Just give me a minute. Da-da-da. Where is the pop quiz? There it goes. Okay. Okay, so if you go to your Canvas, you will find there is a pop quiz number 6. Today is April 27, right? Yeah. Pop quiz number 6. Please go there, and if you are ready to enter the quiz password, say yes to this poll. We'll wait for 1 minute so that everyone on the same page. "13 of 19 said yes. 14 of 19. 4 more people to go. 15 has done yes. 16. 3 more to go. 2 more to go. Okay. So here is your passcode for the quiz.
Professor?
Yes.
Professor, hi.
Yeah.
I don't know if this is just me, but I have a question that doesn't have like a line to answer in.
Okay. You can send me an email after the quiz.
Okay.
Okay. We'll take care of that.
Hi, Professor.
Yes.
I accidentally clicked out before I could paste my password.
Oh, so you don't see the password anymore?
No. Is it possible? Like,
Yeah, let me just. Let me see if I can send it over chat. Let's say. There's a chat here. Hey, what's your name?
Aditya?
Aditya?
Yeah.
Okay. Mhm. See if you can use that.
Yeah. Thank you.
Professor,
Yes. No.
question 9 has no way to answer it. Like,
Yeah,
there's
just
no
send me,
physical.
yeah, send me that. That's probably a glitch in the system. Just send me an email. I'll adjust point. Okay. I think for most of you, time is up. Let's see.
Professor,
Yes.
did he tell us to email you the answer for question 9?
No, yeah, you can send me the answer, but just send me which question you had the issue, and I'll take it. Okay. All right. I'm just trying to look at the quiz statistics for you. Okay. Not very promising. Let's see. So this quiz, you see your high score 90, good. Average score 47%, which is really not good. Like really 50% is the median about that. So please pace up your study. I know this is like end streak of the whole semester, and you guys have a lot of assignment dues for all the different courses, but please make sure you keep the pace up. All right. Any question before we close tonight? Any question at all from anyone on any topic? No? Okay, good night then. And
Wait, Professor?
Raul.
Yeah, in the two's complement form, could you walk through it again? Like, how come? I mean, wait. What I want to ask is, if you have a binary number and you want to convert it into two's complement, the procedure is to logically invert all the bits and then add 1 to it.
Yes.
I was wondering, what's the proof for it? I understand that it works, and I kind of intuitively try to make sense of it by just assuming two's complement of positive 1. If you take all 0, then you're going to get 1 over 1 and one final 0, and you need to add one extra 1.
Right. So proof of the two's complement through the procedure like inversion plus 1 is two's complement. That's what you're asking for?
Yes. What's the proof of it?
That's a good question, and I don't have the answer as of now. And this is a part of the, I think this is the paper they have published initially for two's complement format proposition. And they have all these proofs there. Like this is like a mathematical, logical this theory discussion, and this is not. This is, I think, by definition. Two's complement is a definition of a format. How do you want to represent negative or positive numbers in that format? And then we need to actually look back at that original paper who proposed it.
Okay, I see.
Okay.
I thought it. Yeah. All right. Thank you.
This is by definition of two's complement form. Okay, then. Good night, everyone.